This video is about free energy. By the end of this video, you should understand how to use free energy to determine spontaneity, be able to calculate delta G from delta H and delta S values, be able to calculate delta G from standard values, understand how free energy relates to equilibrium, and calculate K from delta G values. As we saw previously, spontaneity of a reaction depends on entropy, enthalpy, and temperature. Therefore, free energy was developed as a function that helps us deal with entropy, enthalpy, and temperature all at the same time. Gibbs free energy, abbreviated capital G, is defined as the measure of the energy available to a system. G is different than enthalpy because G takes into account the change in entropy, whereas E, enthalpy, assumes that entropy is constant. The equation relating delta H, delta S, delta G, and T is shown here, with temperature in Kelvin, delta G and delta H usually in kilojoules, and delta S usually in joules. Of course, you can't subtract joules from kilojoules, so you'll need to be careful to convert units when doing calculations with this equation. Relating free energy to spontaneity, we find that a process is spontaneous in the direction in which free energy decreases. Therefore, a spontaneous process must have a negative delta G. Conversely, non-spontaneous processes must have a positive delta G. Using the equation delta G equals delta H minus T delta S, consider the fact that if delta H is negative and delta S is positive, we'll always be subtracting a positive value from a negative value. This will always result in a negative delta G, and therefore these reactions will always be spontaneous, regardless of the temperature. Recall that temperature is in Kelvin, so it has to be a positive value. This is consistent with what we've seen before, since negative delta H's and positive delta S's are both thermodynamically favorable. Therefore, these reactions are spontaneous under all conditions. Skipping to the bottom of the chart, when we have a positive delta H and a negative delta S, our delta G will always be positive because we're subtracting a negative from a positive. Therefore, these reactions will be non-spontaneous at all temperatures. Looking at the middle two cases now, recall that we said before that when delta H and delta S have the same sign, we can't predict the sign on delta G unless we know the temperature. Consider then that if they're both negative, it will be spontaneous at low temperatures because as T goes down, we're subtracting a smaller and smaller negative number from delta H, giving us a negative delta G. Conversely, when they're both positive, as the temperature gets larger, we'll be subtracting a larger and larger number from our positive delta H, giving us a negative delta G. Here's some examples to try on your own. Pause the video here, and when you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice that in all but two cases, we were able to predict strictly from the signs whether or not delta G would be positive or negative. In the other two cases, we had to consider what values of T will result in a negative delta G. It's also possible to calculate delta G using standard values, since delta G, like delta H and delta S, is a state function. The equation is shown here. This is math you've done before, so I'm not going to go through an example. You might be wondering then, why would a non-spontaneous or a non-thermodynamically favorable reaction ever occur? Well, it's possible to get these reactions to occur by continually adding energy. Some ways to do this would be adding electricity continuously. For example, a battery will not spontaneously charge itself, but if we add a constant stream of energy, the battery will become charged. Likewise, light is used in photoionization of an atom and in photosynthesis. This allows a non-spontaneous reaction to occur because it continually adds energy to the system. Another way often found in biology is coupling to a favorable reaction. In cases of coupling, one reaction will release free energy that then can be used by the non-spontaneous reaction to occur. Take this example. In this case, the free energy released by the oxidation of glucose, a spontaneous process, can be used to drive the non-spontaneous process of converting simple molecules into more complex molecules. It's also possible to have a spontaneous process that does not occur. This is the case when a reaction has a high activation energy. In this case, we say that the reaction is under, quote, kinetic control. We would have to provide some activation energy in order to get this reaction going. Noting that adding the activation energy is different than adding energy throughout the process. Once the process gets going from the activation energy, no more energy is required if the reaction is spontaneous. Prior to this, we've been looking at free energy and spontaneity of reactions that go to completion. Let's consider free energy in the case of equilibrium. Reactions will proceed to equilibrium when the equilibrium position represents the lowest free energy value, or the most thermodynamically favorable state available to the system. This means that the equilibrium position has a lower free energy than the reaction would if it went to completion. Here's a diagram to help us understand this. Previously, we were looking at situations where 100% products was the lowest free energy state. However, if a reaction has a free energy state lower than that of 100% reaction or 100% product, it will establish equilibrium. We can relate the change in free energy to our equilibrium constant via the equation shown here. In this case, K is our equilibrium constant, T is our Kelvin temperature, and R is the gas constant. Be sure to use the right form of the gas constant. These values are on your equation sheet. When you're using this equation, you want to be sure to use the R value with the unit joules per Kelvin mole. Here's an example problem to try on your own. Pause the video here, and when you come back, I'll reveal the answer. Note that before plugging values into the equation just shown, you'll need to calculate delta G for the reaction. Welcome back. Here's what you should have gotten. Using the difference between the free energies of reactants and products, we calculated the delta G for the reaction, which could then be used in the equation to solve for our equilibrium constant. This value is reasonable since it's quite a small K value, and we know that AgI is only slightly soluble. To generalize, when delta G is negative, this tells us that our K value will be quite large. This is because the products are lower in free energy. Therefore, the equilibrium position must lie closer to the products. This means that the forward reaction is more favorable and products are lower in free energy. One way to think about it is that it's more spontaneous in the forward direction than in the reverse direction. Conversely, when delta G is positive, our K value will be quite small, because the reactants are lower in free energy, so the equilibrium position lies closer to the reactants. The reverse reaction in this case is favorable, and the reactants are lower in free energy. Again, one way to think about this is that the forward reaction is less spontaneous than the reverse reaction. So let's summarize all this G, H, and S information we've seen in the past few videos. First, we found that thermodynamically favorable processes are processes that will decrease the enthalpy of the system and increase the entropy of the system. We also found that spontaneous processes must have a negative delta G. And finally, we found that delta H, delta S, and delta G, because they're all state functions, can be determined stoichiometrically, by subtracting values of reactants from products, by Hess's law, and using delta G equals delta H minus T delta S. These are the main takeaways from the last few videos. That brings us to the end of this video. Let's review our goals. First, we looked at what free energy is and how it relates to spontaneity. Then we looked at how to calculate delta G from delta H and delta S, and how to calculate delta G from standard values. Then we looked at how free energy relates to equilibrium, and finally we learned to calculate K from delta G.